Hello, my name is John Sylvester, and this is joint work with Marcos Kiwi and Marcus Sherpas. So the hyperbolic random graph was introduced by Kurylev as a model for real-world complex networks, and they showed experimentally that this random graph model exhibits many real-world traits. The image on the left is from their work, and where they demonstrated experimentally that it's a good model for the network topology of the internet. Okay, so what is the model? So it's got two parameters, alpha and nu, which are tunable. Alpha is very important, nu not so much. So we start with a hyperbolic disk of radius r, and then we place, this is in the native model of the hyperbolic plane. So we have this disk and we place points in it randomly according to a Poisson process with this density. And notice this is in polar coordinates and it does not depend on the angle, only on the radius. And if you look at this long enough, you'll see that if alpha increases, then points get kind of pushed out to the peripheries, and for smaller alpha, they group closer to the center. And this makes a difference because you then connect two edges, two vertices by an edge, if they're at hyperbolic distance at most r. So in particular, if you drop a point in the dead center of the disk, it's connected to every other point. But as you get out to the edge in this model, hyperbolic distance blows up with Euclidean distance. So some points which appear close in Euclidean distance, if they're near the boundary, they can be very far in hyperbolic distance and not necessarily connected. So this alpha, it has a profound effect on the topology of the network. But for alpha between 0.5 and 1, it proved that the HRG has a power law degree distribution with this natural power law between 2 and 3. So really, arguably, this is the most interesting regime for this model, as outside this, you don't have that. And again, in this regime, with high probability, there's a unique linear-sized giant component. And one thing I should mention is that if you see this dotted ball in the center, this is a ball of radius 0.5, r/2, sorry. Any 2 points within this center ball are connected. So we call this the central clique. And with high probability, this unique giant component contains every vertex in the central clique. Okay, so early results. I'm not going to read these out, but you can pause and have a look. Basically established properties found experimentally. I went a bit further, looking at structural properties, and then more recently people have studied stochastic processes on HRGs or related models. But what's notably absent from this list, to the best of our knowledge, is hitting or cover times of random walk on the hyperbolic random graph. And that's what we endeavored to study. So a simple random walk is your favorite process. You start with a little agent somewhere at some vertex of the graph, and in each time step, they move to a uniformly chosen neighbor of the current vertex. This is a basic and natural process, and it has many applications in computer science. In particular, it's kind of a primitive for building certain randomized algorithms. Okay, so I'll carry on with another animation of a simple random walk, use it to illustrate some points. So one thing which is of key interest in the study of random walks is the stationary distribution and whether or not you converge to it. So if you converge the stationary distribution, then this says that on an unweighted graph, like in our setting, if you run the walk long enough, then basically if you stop it at some time, then the probability you're at vertex V is proportional to its degree. So we're interested. What we're interested in this work is hitting times and cover times. So the hitting time is the expected time it takes to visit a given vertex. So I'm going to show you 3 variations now. So the most fundamental one, I guess, are between pairs of vertices. So you have ex tau y. This is the expected time for a random walk to visit y from x. So for this slide, I should say, just think of a fixed static graph, and this expectation is with regard to all trajectories of the walk. So so ex tau y. Tau y is the stopping time when you hit y. So how long does it take, on average, overall walk starting from x for you to visit y? And then you have tau pi, e pi tau pi, which is the expected time to travel between two vertices which have been selected independently from the stationary distribution. So that's kind of an average hitting time. And finally, we have t hit, which is the maximum hitting time. So this is just the worst case overall start and end vertices of the expected time to get from one to the other. So in this little example, we first visit D at time 7. Again, so that's the stopping time, but we're interested in the expected time to hit D, which would be the hitting time of D. Another thing we're interested in is the cover time. So this is the expected time with respect to the walk to visit every vertex of the graph. So again, in this example, we visit every vertex by time 10, but what we're really interested in is the expectation of that time. So yeah, so we take expectations in this work with respect to the walk. So on a static graph, that's just a fixed number, just a function of the graph. But we're going to be looking at random graphs, so that itself will become a random variable. And a fundamental tool we're going to use is effective resistance. So here's a quick physics primer. So if you have a graph, you consider every edge as having resistance 1. If you have your two vertices u and v, and you connect a potential difference across them, you induce a current from u to v. And the resistance is proportional to 1 over the sides of the current, essentially. So we fixed the voltage to be 1 here, so it's just equal to 1 over the size of the current. So you have a fixed voltage, and if you can drive more electrons from u to v, the current is larger, and so the resistance must be smaller. Okay, so why are we interested in resistance? Well, there's a beautiful connection between electrical networks and reversible Markov chains. And one consequence of that is this formula. So the expected time to get from u to v and then back to u again is equal to the number of edges in your graph times the effective resistance between those two vertices. And so what I showed you before, it didn't look wholly easy to calculate the resistance, but there's actually a very elegant mathematical formulation of resistance given by Thomson's principle. So you take the infimum over all unit flows from V to U, where a flow is to be interpreted in a kind of a sensible way. You can read this and pause it if you wish. Where your infimum is over all flows, and you're trying to minimize the energy dissipated by that flow, which is basically just the square of all the flows going through the edges summed up. So this is more like graph theoretic, and it's nice to work with. Another thing that makes resistance nice to work with is Rayleigh's monotonicity law, which says basically if you increase any of the resistances at the edges, your effective resistance cannot drop. Okay, so how do we use this? Well, first result we have is that the hitting and cover times are n log n and n log n squared in expectation and asymptotically almost surely, so with probability going to 1, where that probability corresponds to the in the giant, with respect to the giant of the hyperbolic random graph in the regime where you have the natural power laws, right? So how do we prove this? Well, the upper bounds are very easy. So we'll begin with t hit, so the maximum hitting time. This is at most the maximum commute time, which is equal to the maximum resistance times the number of edges by our commute time formula. Okay, so resistance between any 2 points is at most the distance between the 2 points, because by Thomson's principle, you can just send all the flow down the shortest path. But the maximum distance between 2 points is the diameter. So by known results on the diameter and the edges, we have our bound. And the upper bound, then you just apply Matthew's bound, which is well known in the theory of Markov chains. It basically says cover time is at most a log times hitting time. Okay, what about the lower bounds? So these are a little bit trickier. So if you have cover time, so we'll look at the lower bound for cover time, right? So by a strengthening of Matthews bound, if you have any set S in a connected graph, then the cover time is at least the number of edges of the whole graph times the minimum resistance between any pair of vertices in S times the log of S. So, okay, so why is this useful? So if you have just an isolated path of length L, then the resistance between the endpoints is exactly equal to L. There's only one unit flow down the path. So essentially, then by Morelli's multiplicity law, we can ignore what happens in the rest of the graph if we can show there are sufficiently many long dangling paths. Where a dangling path essentially looks like this. It's a path of some length L, which is affixed only at one end to the rest of the graph. And we show that it is present, many dangling paths. So for some constant with very large probability, there are omega n to the constant, so polynomially many paths of length order log n in the giant. So you can take each endpoint of the path as your set S, has polynomial size, and there are log n order resistances between each of these pairs, and that gives you the lower bound. So we should note that this lemma is kind of implicit in some earlier works looking at the diameter. And also this is the constant we can take. So for us it's enough because we just want to show this result up to constant, but can you improve this much? And I think if you want to nail the leading constant of the cover time, you need to understand these dangling paths better than we do currently. So that's maximum hitting time. So worst case overall, end start and end points, and cover times of random walk. What about average hitting times? So we'll begin with average resistances, and this is probably the main body of the work really in this paper. So our first theorem says that, okay, for the same regime, so where you have power law degree distribution on the giant, the expected resistance, so with expectation with respect to the graph, and then you have the average resistance between a uniformly chosen pair in the graph of vertices. This is bounded above and below by a constant. And recall that because of the dangling paths, the maximum resistance between any pair of vertices in the graph is of order log n. So this is kind of analogous to what happens with distances. So for distances, but it's a little different because for distances, it's been shown actually that the average distance is log n. So not constant, but log n. And the maximum distance, again, by this dangling paths, is at least log n. And the upper bound on the diameter, showing that this log n is tight, was only recently proved after a series of several papers. Okay, so in the max case, with the diameter and the max resistance is the same, but with average distance, you have log n versus constant for resistance. So what's happening is, yes, the diameter is average diameter is log n, but between any 2 points, you can actually find many mostly edge disjoint paths of length log n or slightly larger between the two vertices. And so what happens is the current can actually split up over these different paths, and so you're not sending too much flow through too many edges, and your resistance actually is constant. So this effective resistance is kind of it's not just about shortest paths, it's about how many paths and how well you can flow through the network. Okay, so we can use the nuts and bolts of this first theorem to show that the average hitting time, so hitting time between two vertices from the stationary distribution, is of order n. So essentially there you have average hitting time order n, max hitting time order n log n. Okay, so how do we prove this? We adapt a tiling of the half plane due to Fuld, Larkison, Muller to work with the native model. So the Funtalakis and Muller tiling is very nice, and it has very nice properties that we'll see in a minute. But they came up with this tiling in the half plane. However, the model, the HRG, is not described in the half plane, it's in the native model. So you need to rely on a coupling between the two models, and so you lose some probability in doing so. So in particular, this no result you prove using the tiling of the half plane will hold with probability any greater than 1 minus n to the c for some unspecified small constant c. Whereas, so we hope this is one of the main contributions of our work, is this new tiling. So it has the same properties as Funtalakis Muller tiling pretty much, but it works directly in the native model. So, so if you prove something holds with probability x, it does hold with probability x in the HRG. Okay, so if we use this tiling to come up with a nice flow, which by Thompson's principle gives us an upper bound on the resistance. So what are the properties? So if you have 2 points in the same tile, they are at distance about r, thus connected. And we think of each tile as being composed of 2 half tiles. So if you send a ray from the center of the disk to the periphery, and it cuts the tile in half, they're your 2 halves. And if you look at the half tiles, they have a kind of tree-like structure. So think of the root as being at the origin, the center of the disk, and then you have many half tiles coming from the roof. But each half tile, if you move out towards the edge of the disk, it has 2 children half tiles, right? So two half tiles that are below it. If you think of the root as being the top. And any point in a tile is within distance at most r from any point in its parent, so thinking about the tree going back up to the root, in its parent half tile. So this is very nice as well. So the 2 main properties are at the top and bottom really. So any 2 points in a tile are connected, and any point is connected to every point in its parent half tile. So how do we use this to come up with a nice flow? So let's say we have these 2 vertices. We want a flow between them. Well, as I said earlier, this r/2 central radius ball in the middle, everything is connected to everything else within this ball. So essentially, you just need to worry about your flow that goes from your start or endpoint into the center. And trust me that once you're in the center, everything matches up nicely. So let's look at a flow from U to the central cleat. Well, say we have, we start at U, we want to distribute flow as evenly as possible over the tile we're currently in. So each vertex then has the same amount of flow arriving into it within one tile, and then you spread flow evenly from each vertex in that tile across the vertices of the parent half tile. Okay, so moving kind of one step closer to the center, and then as soon as you're in this situation, you basically do the same again. So you've now got half the tile has an even amount of flow spread over the vertices, and you make flows to the other half of the other half of the tiles, the vertices in there, so that the flow is evenly spread. And then you go up to the next half tile, and you keep doing this until you get to the central cleat. So this is the rough idea of how you build a flow, but certain things can go wrong. So in particular, every tile involved in this needs to be non-empty, otherwise there's no flow. But what's more, they need to actually have a suitable amount of vertices in them. So if you don't have enough vertices in a tile, then the flow can become pinched, where you have too few edges going to and from that tile, and you're putting too much flow through them, and it contributes too much to the overall energy dissipated. So essentially this happens, or rather every tile in your ancestors going up to the root is suitably dense with probability constant if the start vertex is a constant away from the boundary of the disk. But the problem is here that the average vertex kind of is a constant distance from the edge of the disk. Right? There are a constant fraction of the vertices lie at constant distance from the edge of the disk. So making this work is quite technical, and it depends on the tail probabilities quite a bit. So how fast this probability decays as a function of how close you are to the edge of the disk. But there's not time to discuss this, but all the details are on the archive. Anyway, so we can use that to control the average resistances, and in turn we get the average hitting times. And just to recap, we got the maximum hitting time and cover time. So I should mention that the first result only holds with expectation with respect to the random graph. It'd be very nice to have this working also asymptotically almost surely, and that's work in progress at the moment. Hopefully that will be on the archive soon. And also we're working on coming up with tighter bounds for the resistances as a function of the degrees of the vertices of the source and sink. So in particular, we can show if the vertex's degree is large, so super constant, then versus source and sink, then the resistance is little o1. But more detailed than that. Future work, look at other random walk quantities, such as meeting times. Also, it would be nice to nail the mixing time of the hyperbolic random graph. So this is known up to polylog factors in the HRG. It would be nice to remove those polylogs. There was some work recently on scale-free percolation, where they made progress on mixing times and nailed it, certainly in certain regimes. It'd be nice to get the exact mixing time for the HRG. Okay, and also sharper estimates on the cover time. So I'd like to know that cover time is, some constant times n log n squared with high probability. But I think there are several technical challenges involved in doing that. So, thank you.